Okay, so to start off, I want to talk about this maybe, let's say, recent switch from thinking about codes to circuits, which I think is something that a lot of people know about. And maybe you can say that this was kicked off in 2021 by this paper by Hastings and Parr on dynamically generated logical qubits, where you have a code that kind of naively has 0 encoded qubits, but then if you measure the check operators in the right sequence, you get a logical qubit. And then this kind of inspired a lot of follow-up work on these Floquet codes, and then there's also these interesting papers there's this one by Matt McEwen and others where they think about the syndrome extraction circuits for the service code, but instead of kind of thinking about the starting code, they think about the code in the kind of, you track the evolution of the stabilizers until the middle of the circuit, you think about this instead. And then these were then used by Barbara Terhal and Mackenzie Shaw, they called them morphing circuits. But I would say that maybe this is maybe a recent switch, but it's also got some kind of older history, because I think you can think about measurement-based or later kind of fusion-based quantum computation as perspectives on fault tolerance that are really to do with protocols and not to do with codes. So although this is kind of a recent thing, I would say, there's this long history, especially coming from MVQC. And the question I wanted to kind of ask is, in this modern world of circuits, not codes, well, then how can we say that two circuits are the same? And by the same, I kind of mean, I want to know when circuits are the same from a fault tolerance perspective. And this is the kind of key question that I want to try and answer today. And in this paper that I'm going to talk about, we had an approach to providing an answer to this, and I'll just give you a very high-level overview of how that works. So the idea is we have a circuit, but then we're actually going to represent it as a code. And we're going to use this Spacetime codes formalism, which I'll explain. And then we have this code, and then we want to, instead of thinking of it as a code, we're going to think of it as a chain complex. And, well, why do we want to do this? Because then we can think about the natural kind of maps between chain complexes, which are called chain maps, and then we can define a kind of chain map that preserves the fault-tolerant structure. And then we'll use this to kind of answer this question of when can we think about two error correction circuits being the same. And why is this something we want to do? I mean, it's kind of interesting, but is this actually useful? So I think one thing you can do with this kind of approach is to take an abstract UEC protocol defined in some language and transform it to a different model. So there's nice examples of this, of taking a circuit-based protocol, so you've got some UEC thing and you've defined it in the circuit model, but now I want to translate this to measurement-based quantum computation, for example. And this was actually the main motivation when we first started on this project, because this started when I was still working at Xanadu, where they want to do measurement-based quantum computation. And more abstractly, this is about kind of changing the compilation of a quantum error correcting circuit. So you have like this kind of abstract circuit or written in some language, but then you have a device or hardware platform with some kind of native operations you want to translate from one to the other. And then the last thing that you can think about with this is that if you have this map from kind of one circuit to another that preserves the fault tolerance properties, one of which will be the decoding, kind of the decoding structure, then it means that you can sort of transform decoding problems into one another, and you can, in a sense, take a hard decoding problem maybe and map it to an easy one. And now I just want to kind of acknowledge some references and some things that inspired our work. So on this kind of decoding question, there's this nice series of work which uses this relationship between the color code and the toric code, where you know that a color code is essentially equivalent to some number of copies of toric code, and you use this to decode the color code. Because in the color code, let's say in 2D, you have this problem where my error will cause 3 syndromes, so I can't use matching anymore. But then if I map to toric code, then I can use matching, so I can do the decoding. And then these nice papers by Delphos and Qubits as well, and many others. And we're also kind of building on this results of foliation of quantum codes, which is an idea where I take a CSS code as input, and I have a technique to produce a fault-tolerant measurement-based protocol from this. And you can see this is kind of an early thing of taking a circuit model kind of idea and translating it into MVQC. And then there's also been a very nice line of work on circuit protocol equivalence using the ZX calculus. So There's this nice paper from Quantum where they kind of showed that for topological codes, you can think of like Floquet codes, MBQC, FBQC, and circuit-based as all kind of one different expressions of the same fault-tolerant structure. And there's also this work on Floquetifying code, so I have some static code, and then I want to find the Floquet version. And then also there's this nice recent line of work by Ben Rodutz and Alex Kissinger and others in Oxford, where they're taking ZX calculus, which, as you probably know, is a set of kind of diagrammatic rewrite rules for quantum circuits. But then they ask, when can I have rewrite rules that kind of preserve the fault-tolerant structure? And I think Ben gave a talk about this at QIP last week. And this could be very nice, I think, in the future for also kind of having some automated tools for doing this kind of thing. So I just wanted to flash up these references. And yeah, so these are, I think, especially this last one is quite related to what we're doing. And I'd be interested, if someone wants to talk about that after, I'd be interested to discuss. So after that intro, here's like an overview of the rest of the talk. So I'm going to take you through this procedure I kind of sketched. So we start from some circuit, we transform it into this subsystem code, then we take the subsystem code and represent it as a chain complex, and then we define these fault-tolerant maps. And then I'll end by talking a little bit about some applications that we did and some future ideas. And yeah, please, if you have any questions at any point, just interrupt me. Okay. So I want to start by talking about spacetime codes, which is another kind of recent idea but actually has some history. So this is an idea where we start from some Clifford circuit, and then we have a way to associate a code to this circuit. And this actually comes from over 10 years ago, this paper by Bacon and others. And they show that if you start from kind of a Clifford circuit under some restrictions, that you can map it to a subsystem code. And then there was a more recent work by Delphos and Pacenik where they have a mapping from a Clifford circuit to a stabilizer code. And then it's actually also really related to what STIM is doing under the hood. When STIM constructs a detect error model for you, it's basically doing a version of what I'm going to represent. And so in the paper, we kind of provide a perspective on these things, which sort of maybe synthesizes a few elements from these different approaches. Okay, so just before I get into how the space-time code mapping works, I want to just give a recap on subsystem codes, just to make sure we're all on the same page with regard to them. So you can think of it as I have a stabilizer code, and I take some subset of the logical qubit and I gauge them out. So by that I mean I don't use them to encode information anymore. And so then this kind of code will be defined by some gauge group, which is a non-abelian Pauli subgroup now. And you can think of this as taking, I have my stabilizer group, and then I have some qubits, logical qubits I don't care about anymore, and I'm sort of adding the logical operators of those into the stabilizer group. And then this will give me a non-abelian group, because obviously I have X and Z operators for the qubits. And there's many ways we can use subsystem codes, like, but what I'm really interested in this aspect today is that the reason we wanted to use subsystem code is because when we construct the spacetime code, we'll have lots of low-weight logical operators, but we wanted to throw them away. And so this gives us a systematic way to do this. Okay, so let's get into the construction. So we have an example circuit here where we have 4 qubits, one of which is initialized in the 0 state. I have some CNOT gates, and these M's are just measurements. And the first thing I do is I introduce some kind of coordinate system for the circuit, so every qubit gets a label and each time step gets a label. And then now when I have this, I can think about a space-time Pauli operator. So I can think about a Pauli operator acting at a specific qubit at a specific time. Okay? So that's like step 1 is just the coordinate system. Okay, and now let's talk about some other things we can define. So in the Bacon paper, they describe this thing called a spackle, which I think it comes from like some kind of wallpaper paste thing when you spread wallpaper paste. It's a word that I wasn't aware of, but anyway. So you have a spackle, and I guess I'm not a DOI expert, but we have this operator XZ here, which is kind of the measurement operator, and the spackle is just that I take this operator and I propagate it through the circuit. So you see when that X, let's try this. When this X hits the CNOT, it propagates to X on the target as well, and when a Z hits the CNOT, it kind of just goes straight through. And the rule is that to propagate past measurements is just like they weren't there. So we can define the spackles of operators, and then we can also define something called an outcome code check. So this is just the observation that in QEC circuits, the way we do error correction is that we have some subset of measurements whose value should be deterministic in the absence of noise. So in this circuit here, the measurement outcome of this one plus this one plus this one, when you think of them as binary variables, should sum to 0 and 1, 2, because you can kind of see that it's a bit like when I repeat the stabilizer measurement, but it's a bit more complicated because this is kind of been conjugated by the C0. But you can see that if I get a measurement outcome here, it should match the sum of these two. And then what we'll call a detector in the spacetime code is I take the spackles of these three measurements and I multiply them together as Pauli operators. So this one, as we saw before, we have this kind of tail coming out like this. And then when I multiply the spackles off, so I have this one and this one, that will just cancel the Pauli operators kind of coming here and here and here. And so then what I get in the end is this set of 5 Pauli operators. And now this is now telling you, so if you're familiar with STIM, this is kind of like a detector, and this is telling you which errors will flip this detector value. So I know I have this measurement, so I expect them to sum to 0, and then I know now that if I have an X error here, for example, it will flip this. And so this is how you kind of build up the detector error model. So this is kind of like a very high-level summary of how the Delphos presentation, Delphos basic presentation of spacetime code goes. But the one issue we had when using their construction was that we ended up with a lot of low-weight logical operators. So we decided we wanted to go the subsystem code road, and now I want to tell you how that works. So the things that were kind of causing problems are what we call elementary propagation operators. So this is just like if I have a unit tree, like I have this Hadamard gate here, then I just think about Pauli X and Pauli Z before the gate and how do they propagate through the gate. So X goes to Z, Z goes to X, and I can define these things for all of my unitary gates where, for example, in this control Z, I have an X before maps to X, and then I pick up a Z. And also there's some rules for defining them for measurements and state preparation, so I won't go into that. And so these operators are kind of, if we think about this, the space-time code as a stabilizer code with the detectors of the stabilizers, then all of these elementary propagation operators actually commute with all the stabilizers. So, but they're not stabilizers themselves, so hence they would be logical operators. But we don't actually want that to happen because these are all low-weight operators, and they're not really telling us about the error correction properties of the circuit. They're just telling us about like the propagation through unit trees. So what we do is we think about a subsystem code where the generating set is just given by all of these elementary propagation operators like this. So you have them for every single gate. I define one for every measurement. I also define one for state prep for that. Yeah, that's it. And then the non-trivial thing to show at that point is that, okay, now we've defined this subsystem code, now we can show that if I take this spackle operator, then this is actually a gauge operator. Then I can say, okay, the stabilizers for a subsystem code, I basically take the center of the gauge group, so everything in the gauge group that commutes with everything else, and I have to mod out complex spaces. Then those stabilizers, I can show that they're the spackles of measurements, and also the detectors correspond to stabilizers. So this all kind of makes sense in that what we want to use for error correction in our kind of detector error model are actually stabilizers of this subsystem code. And then finally, there are also logical operators that are spackles of certain things, but I won't go into too much detail about what those are. But I just wanted to show you that the idea here is that we have this method for mapping any Clifford circuit to the subsystem code. Okay, let's look at an example. So in this circuit here, we imagine that so this SXX means, imagine that we start off in a stabilizer group just generated by a two-body X operator, and then we have this kind of sort of trivial circuit where we apply some Hadamards, then we measure the stabilizer again, and we apply some Hadamards, we measure again. And so then if I think about the detectors of this circuit, well, if I start in this +1 eigenstate of XX, and I do Hadamard twice, when I measure it again, I should get +1. So then this measurement should just be kind of 0 interpreted as a binary variable. And similarly, I can think about if I measure this here and then I measure it again here, I should get another stabilizer because these measurements should match. And so then I can form these stabilizers by taking the spackle of, like, for example, the spackle of this one here, this measurement, oops, this we'll just go and propagate x at x and x, and then I take the spackle this one, and I kind of cancel these x's, so I'm left with this 6-body operator here. So this is kind of a kind of relatively simple example that shows you how everything works. And then if you're interested, the logical operators will also come from spackles. So for example, what I can do is think about, if I think about this input state as being stabilized by xx, then this is this I can think of this as a code, and it will have a single logical qubit. So the logical x operator would just be a single qubit x. And so the way to build a logical operator of the spacetime code is just to spackle this one. So I just propagate it through, and I just get this pattern of x's and z's. And then similarly for this kind of simple code with just an xx stabilizer, the logical z operator is just a 2-body z. And then I can actually spackle this to get the logical operator, but I can actually notice that I can reduce its weight to just this by multiplying by stabilizers, basically. So this just gives you like a high-level example, so you have a good picture in your head of how we do this. So the idea, we start from any circuit, and then we can build this subsystem code on top of it in this deterministic way. And this subsystem code is kind of capturing the error correction properties as basically a formalization of the detector error model. Okay, so are there any questions about this step? Moving on then. Now I want to go from a subsystem code to a chain complex, and I think the mapping of, well, the equivalence, let's say, of CSS codes and chain complexes is very well known. This idea of doing it for subsystem code is, I'm not sure if, I haven't actually seen it before in the literature, but I think it's kind of some folklore thing, so I think people do know about it. But the idea is this: we're going to think about this chain complex, and I'll explain what all these things are just now. So we have, again, a 3-term chain complex. It's a chain complex with 2 maps. And so I have my gauge operators here, which is just, so I have, let's say, MJ generators, the gauge group, and then I take this Z2 vector space. Then I have my errors, which I have this Z2 vector space. Now, this has got 2 times n, where n is the number of qubits basis vectors, and that's because we're considering this in like a binary symplectic format. So we're keeping track of both the x and the z components of the error. And then finally, we have these syndromes, which are here, and then again, this is just like some Z2 vector space with ms number of generators. And now for the maps. So the first thing I have is this gauge matrix. So this is like a matrix, again, in binary symplectic format, where each row is basically a gauge operator. And so when I apply this map, it's telling me about the support of the gauge operator on the qubits. And then I also have this stabilizer matrix, again, which is just the parity check matrix of the subsystem code. But I get this symplectic matrix here. And what this is doing is it's just taking care of the fact that I have let's say I have an X error, but this is going to trigger the Z stabilizers. So when I apply the matrix, I kind of want to exchange X and Z. It's more of a conventional thing to set up this way. But that's all that's doing. It's just taking into account the fact that the X stabilizers anti-commute with the Z errors and vice versa. Okay, and so if the stabilizers and the gauge operators should commute, because the stabilizers are defined to be the center of the gauge group, and so that corresponds to this equation here. And again, I'm using this symplectic matrix to kind of overlap the X part of the gauge with the Z part of the stabilizers. And this being 0 is equivalent to this chain complex condition where the boundary of boundary is 0. So what I've kind of showed you here is that for any subsystem code, I can represent it as a chain complex. Now, this is not actually as nice as the case for CSS code, because it's not the case that every chain complex can be represented as a subsystem code. And why is that? It's because there's a constraint between these 2 matrices here, basically because the stabilizers must be expressible as gauge operators. And so that constrains these things. So I can't just take any chain complex and say it's a subsystem code, but for any subsystem code, I can represent it as a chain complex. Okay. And yeah, for the experts, maybe there's also, the homology of this will tell you about the logical operators of the subsystem code. So there's these things called dressed logical operators. So these are things that commute with all the stabilizers, but are not themselves gauge operators. And there's also these things called bare logical operators that correspond to things that commute with all the gauge operators, but are not stabilizers. But we won't actually use this. I just wanted to flash it up there so you know that the homology also has some interpretation in this. Okay. And now so that was the general case, and now we can talk about CSS codes, where it kind of simplifies a little bit. So if I have this now in the CSS code, I have this split between the gauge operators into Z and X type, same with the errors and the syndromes. And then you see also the matrices will split up as well into the X and Z type. And then you can kind of see here that this omega is getting taken care of the fact by the X part is kind of acting on the Z here. So the X syndromes come from the Z errors, and the X and the Z syndromes come from the X errors. And so really, like, I can think of this as just two chain complexes like this, and yeah, so I can think of just separate ones for X and Z in the case of CSS, in the case of a CSS subsystem. Okay, so this is a relatively heavy. So let's think about an example. So we're going to use like a graphical representation of subsystem code. So what I have in this graphical representation, I have three types of vertices. So I have circles that are gauge operators, triangles that are stabilizers, and then squares, which are qubit errors. And so what this is saying is that, so in this code, I have 16 qubits, and this is representing the possible Z errors on the qubits. And then I have gauge operators, which are like two-body. So this is a ZZ gauge operator, so it's kind of the adjacency. It's representing the adjacency of the gauge kind of check matrix. And so you see I have all these two-body Z gauge operators, and the stabilizers, this one is an 8-body stabilizer, like this. So this would be like the kind of one half of the subsystem code where I'm talking about, it's actually, so the Z errors, the Z gauge operators, but the X stabilizers, or the X syndromes, let's say. And then I also have this one, which would be the X part. So now I again have two-body X gauge operators, and then I have the X errors, and then I have the Z syndromes. And then pop quiz is like, which code is this? Making sure, yeah, very good. Yeah. So the kind of the very nice example of a subsystem code, but this is how you represent it in this language. Okay, and we're going to use this graphical, define all our kind of maps in terms of this graphical picture. Okay, yeah, so are there any questions about this part? Yeah?
So earlier you said that not all chain complex can be represented in this form, but can't I just put like the stabilizer matrix on either side and then like, then wouldn't that give the form? Like, it's trivial, but...
Oh, okay. Yeah, I think I see what you're saying. Yeah, if it's true that, like, yeah, I can basically, if I make the gauge group abelian, then I can always do it, that's right. Yeah, so that's right, every chain complex does correspond to a subsystem code, but some of them will be kind of trivial where there's no additional structure, it's just a stabilizer code. Yeah, that's right. Okay, so now I can get to the kind of meat of this talk. So I want to talk about fault-tolerant maps. And first thing I need to define is a chain map. And basically, we have this structure here. So I have two chain complexes, let's say C and C prime, where I have these three spaces and these maps. And so you can think of this in your head as two quantum codes. And then I have these three maps here, F0, F1, and F2. And these are maps from kind of the 0 dimensional to the 0 here, the 1 to the 1, etc. And a chain map is just a set of maps like this, such that this diagram commutes. And yeah, so that just means that, you know, it's equivalent for me to go this way and then like this, or I could go down first, down here, and then across like that. This is not the easiest points to use. Yeah, like this, like this, or I could go this like this. And so these are objects that are like very well studied in homological algebra. They're the kind of natural map for chain complexes. And we also are going to think about something that's a bit more restricted, where there's something called a quasi-isomorphism. So this is just a chain map that induces an isomorphism on the homology. And in the quantum codes language, that just means I preserve the kind of number of logical qubits in the structure. So this is like a map from one code to the other that preserves the logical information. Okay? And now we want to add some additional constraints on these chain maps to preserve more of the QEC structure. So we take a quasi-isomorphism and we impose two additional properties. We want the distance to be preserved. So there's like a notion of the distance of the chain complex and the notion of the distance of this one, just given by the homology groups and the lowest weight representatives. We want this to be preserved. And in STIM, this is what people would call the fault distance. And then we also want decoding preservation. And this is a bit more complicated to state, but so let's imagine we have the minimum weight decoding functions for these two chain complexes. And what this would mean is that, let's say I have a syndrome in C0, then I have a function x that takes me from C0 to C1, and what it returns is the minimum weight element of C1, which has the syndrome that I observed. And I would have similar for x prime. And now, decoding preservation, we define it to mean this. So basically, let's say I start from C0. It should be equivalent for me to do the minimum weight decoding in the first code and then map to the second code. But I should also be able to instead map to the second code and then do the minimum weight decoding there. So this should be equivalent, and then this is kind of telling me that basically if I solve the decoding problem in one code, I've solved it in the other one. And so this is actually, okay, let me just let that sink in. But this is actually quite, it's quite a restrictive definition, this one. And actually, I'll talk in the end about how we can maybe relax this. But yeah, it's quite strong, really, that's saying that if I can do minimum weight decoding in one code, I can actually do minimum weight decoding in the other one. But we wanted this because this is maybe the strongest thing you kind of want for preserving the decoding problem. So if we have these conditions, then we know that kind of like, when I map from one chain complex to the other, from the QEC perspective, not much has really changed. Because the number of logical qubits is the same, the distance is the same, and I can also decode it still. Okay. Right, so now I can tell you about two examples of fault-tolerant maps. The first one is we call rule A, and I'll write them in terms of this graphical language. So what you can interpret this as is that I have this 2-qubit gauge operator here, and then I'm allowed to kind of merge the 2 qubits in its support to a single qubit here. And you can kind of see maybe that this won't change the distance, basically, because if I have an error here, it's kind of equivalent to one here. If I have a 2-qubit error, I can just remove it. So you can kind of see that that will be true. But proving that this satisfies all of those definitions is one of the things we have to do in the paper. But it's quite like a simple rule, and one that you can maybe believe would be a fault-tolerant map, as I described. And then the second one is what we call rule D, and this is perhaps even simpler. So this is saying that if I just have like a qubit in the support of just a weight 1 gauge operator, I can just kind of remove this from the code. And you can see this as maybe that this qubit is kind of just getting fixed by this gauge operator, so it doesn't really, it's not really relevant to the properties of the code from a QEC perspective. Okay, so these are two kind of atomic fault-tolerant maps that we show satisfy the definition. And they're kind of simple, but it's surprising what you can actually show with them. So let's go back to our Bacon shortcode example. And now let's think about, so we have this fault-tolerant map here, which is, if I have a 2-qubit gauge operator, I can kind of like merge the 2 qubit errors here. And you see that we have like a lot of structure of this kind in this code. So I have all these weight 2 gauge operators, and I can kind of merge them all along, in this way along the rows, and in the x1 along the columns. And then if I do that, I end up with these codes instead. And you notice that in this case, these are just repetition codes. And so this is like a way of a graphical proof of the well-known property that I can decode the Bacon shortcode using just like the repetition code decoder. And you're seeing that really, like from a QEC perspective, in this abstract language, these two things are basically equivalent. They have the same distance. I can decode one with the other one, and they have the same number of logical qubits. Okay, and let's look at a second example, which is maybe a slightly more involved one. So I want to show that these two things. Well, I want to show there's a fault-tolerant map from this circuit to this circuit. So this is just our standard Hadamard circuit, and then this is how you can implement Hadamard in like an MBQC fashion. So when you do this, if you have like an input state here, and you apply this circuit, and actually there should be some like feed forward here, but ignore that. This qubit will pick up a Hadamard here. So we want to show that kind of this circuit Hadamard is equivalent to the measurement-based Hadamard. Okay, so how are we going to approach this? So we first write down the subsystem codes for the circuit. So this is quite a simple example here. For this subsystem code, I have two coordinates for qubits before and after the gate, and then my gauge operator is just like x before goes to z after, which is just this one, or z before goes to x after. And then, I have these dangling legs because I could have this could be a sub part of a larger circuit with various inputs, but it looks like this. And then the second one is a bit more complicated, but we can also do the same thing. So now here I have actually 4 qubit coordinates because I have before and after the CZ gate and before for both wires. And so I get 4 qubits, so then I have 8 possible error types of x and z. And then let's just break this down a bit. So I get, for example, for this x eigenstate preparation, I have a single qubit x gauge operator, basically, because it doesn't do anything to put an x error here, because you can just kind of absorb it back to this state. And similarly, for this x measurement, I have a gauge operator here, because I'm kind of allowed to do an x error here, and it won't change the output of the measurement. And then this CZ thing here, well, what it will do, if I have an x error here, it maps to x here by taking the z here. And that's this 3 qubit gauge operator here that has x here, and then z down here. And then I also have a similar one down here for the x and for the z, and they just kind of go straight through, so I get a z like that. And then, so what we want to do is we want to show that we can use a sequence of our rules A and B to transform this chain complex into this one. So it's not actually too hard to do that. So we start from here. We notice that we have some 2 qubit gauge operators here. So I have this ZZ here. So I'm actually going to be able to merge these. And what I'll do is I'll merge this one left, I think, and merge this one right. And then we notice that also we can use rule B because I have these 1 qubit gauge operators from the state prep and measurement. So actually, I can remove these from the circuit and it won't do anything. So if I apply those rules, what I get is something like this. And now you notice we actually have solved the problem because now I just have 4 qubit errors here, and I have this thing where I have an x that goes to a z, and a z that goes to an x, so this is just equivalent to the Hadamard circuit I showed you before. And so all I wanted to do here was just illustrate that using these kind of small rules, we can start building up bigger and bigger kind of circuit equivalences. And we kind of, this is like the first step, and then we keep doing this to prove the results. Okay, any questions about this part? Yeah.
I'm the chair.
Okay, so you're saying kind of fault equivalences there. Something that's kind of interesting about these maps is that they still have a kind of direction to them. Like they're quasi-isomorphisms, but they're not isomorphisms. So you have this this property where you want it to be, if it's decodable, minimum weight decodable on the first one, then it's then minimum weight decodable on the second one. But because it's not necessarily defined the other way, it doesn't seem like there's kind of an inverse to that.
Yeah, you're right. It's a good point that I glossed over this. But in general, these maps are going one way. So if it's not really an equivalence. But then what we actually do is prove the reverse as well.
Okay.
So that for example, in this case, we can construct a fault-tolerant map going the other way as well. So then we actually do have this kind of equivalence. But this is kind of easier to show it for this one, but there exists one going the other way as well. But yeah, that's not automatic coming to the definitions that we have to prove.
Yeah, so I maybe had a similar question about the Bacon-Shaw example. So, in the Bacon-Shaw example, you start out with something that's clearly a quantum code, and although you've separated the x and the z's, there's kind of like qubits.
Yeah.
And then at the end, there's no longer some qubit. That's just 2 classical codes at the end, right? So I suppose one question I could ask about that is surely is not an inverse in that case, or what are the rules here? This is somehow separating. This is somehow extracting 2 classical decoding problems from some original quantum code.
Yeah, it's good. We've actually you're picking up exactly the things I glossed over. But basically, so what I showed you, those rules are not actually chain maps because they're not because of this issue. And so we had to define some notion of something called a weak chain map. So this commuting diagram is not fully commuting in our case, but there's some condition on the images of the matrices basically that needs to come in. And so we can prove all the equivalences with respect to this thing, but I guess maybe this is what's coming in where we have this subtlety. But I would say that the equivalence here is that kind of, if I want to think about, all we're saying about the equivalence is I want to think about how many encoded qubits does this chain complex have, what's the distance of the chain complex, and a decoding problem. But like none of those things are kind of like have anything to do with its being quantum or not exactly.
Yeah.
So then there exist cases like this where I'm kind of mapping from something that looks quantum to something that looks classical. But just from the perspective of the things that I kind of care about from solving the QEC problem, it's just saying that I could solve it on that side and do it that way. But yeah, I don't necessarily, it doesn't necessarily preserve like the quantum structure. Yeah.
So normally for subsystem codes, I would usually demand something like that all stabilizers are, well, at least subsystem codes when I'm using them as subsystem codes for fault tolerance, and yeah, as opposed to like to describe the circuit, I would demand that that every stabilizer is like generated by like a sparse like number of gauge operators. Should I be thinking of that here as well? Like, is this property, do I need this property? And if so, is it preserved?
Yeah, so good question. In general, it will depend on the circuit, whether or not this is true. But it's like, if I constructed the circuit in a clever way, it should be true. So if I have a circuit of something where I'm, measuring like the checks of a LDPC code, like one time, then another time, then another time, all of my detectors will be sparsely generated with the gauge operators. But like, if I did something, if I like forgot to measure one of the stabilizers at some point and then didn't measure it again for ages, then I'd have like a very big stabilizer. But as long as I design my circuit well, I can kind of enforce that. Whether or not this is preserved, so I think under these rules it will be preserved because they're not really drastically changing the weights of anything. But yeah, you kind of want to have some notion of the sparsity of the chain map, and then that will then imply that you kind of preserve LDPC properties up to some like constant factor. Okay, thanks for the great questions. So the last part of the talk, I just want to run you through some applications of this formalism. So the main thing we looked at was circuits to MBQC, and then what we did is, so we just start with our rules A and B, and then we map various different kind of protocols to MBQC. So the simplest one is if you think about repeated error correction with the CSS code, where I just measure the X, then the Z, and the X, and the Z stabilizers. Then this will then map, we can map this to MBQC, and we just recover this result of foliation by Volt and others. And then we can kind of go a bit further, and we look at like non-CSS codes, and then you can recover this, these results of Ben Brown and Sam Roberts. And then you can start going to like subsystem codes and Floquet codes, and then some results here. There's also like, so this paid by Cy Quantum on the kind of topological code case, and then Pezani and Brown did this kind of honeycomb code case for the CSS honeycomb code. But we can kind of go beyond that and look at like any Floquet code or any and non-CSS kind of Floquet codes as well. We have the formalism to handle all of this. And then the other thing we looked at is kind of like transversal gates, which I guess, especially once you start doing maybe full transversal gates, it's not quite as obvious how you should set that up as an MBQC circuit. And so we just did various examples, but yeah, actually the kind of genesis of this project was exactly this part here. So I remember when I was working at Xanadu, they had, when the kind of Hart Hastings paper came out, we wanted to benchmark it in the architecture, and then we took like, so Arthur started his internship and was one of the co-authors of the paper, and it was kind of like a bit of a pain to code this all up manually. And to kind of check everything manually. So what we wanted to come up with was a more robust, systematic way of just saying, say someone invents like a new QEC protocol in the circuit model, then we can just translate it to MBQC, and we have all this guarantee, so we don't need to kind of like do everything by hand and then check everything. And so I think after like years later, we succeeded to do this, but I mean, they'd already benchmarked the thing by then, but it was very interesting along the way. So this is kind of the main application that we did in the paper, and I just want to kind of tell you a bit about how that works. So we start from some Clifford circuit, and we want to translate this to measure-based quantum computing. And so first we do this kind of compilation into a slightly strange gate set, where we think about Hadamard gates, Hadamard followed by S and CZ gates, So this is, I can write all Clifford gates in this way because I can get Hadamard S and C naught from this. And then what we do is we take these H and HS gates and we can map them to the MBQC version. So I showed you an example of a lemma for doing that for Hadamard, and you can also write a lemma for the Hadamard followed by the base gate. And then basically, so in these proofs we're assuming some kind of, it's a bit like phenomenological noise, and in that case, so then we can start doing this thing of merging CZ networks of CZ gates. And what this really means is that we can move to this noise model where you imagine that you're just kind of like given a cluster state at the start, and then there's kind of like single qubit errors hitting it. And this is like the first kind of case you consider. It's like a standard noise model in MPQC, and it's kind of the simplest one. And yeah, this already took like quite a lot of work. It's like nearly 100 pages paper. So it's a good start to do this one. But this is kind of what we ended up showing on the mapping from MPQC to MPQC. But I'd say the nice thing is that it's quite generic, and you know, if we have the rules are just the same for any circuit, we just kind of apply this compilation. And at each step, because we show that these are fault-tolerant maps, we know that we preserve the distance, the encoding problem, everything. So then the thing we get at the end, we have guarantees on this structure. And yeah, the last thing I just wanted to say about is that we use this notion of in the proofs of a cluster state complex, which I won't define today, but I just wanted to point it out as something that's kind of, if you're interested, that's in the paper. So it's a generalization of the cluster state where we now have some input and output nodes to capture, like, if the code starts in like a specific stabilizer group, for example. We also allow for self loops, which allows for Y measurements, which we found useful. And then we can also include like detector nodes in the cluster state as well. And this is just a nice representation that we use in some of these proofs. Okay, so to conclude, just to summarize, so today I told you about fault-tolerant maps, which is a way of taking a quantum error correcting circuit or fault tolerance protocol and transforming it, but having some guarantees about retaining the QEC properties. We found it as a flexible procedure that we could use to map various quantum error correcting circuits, which are Clifford, to MBQC. And in future, there's a few interesting lines that we can cover with this research. One obvious thing is to think about circuit level noise, which I think is eminently doable. It's just kind of more complicated, but I think the same approach would work. Another question is that the requirement we have on the map to preserve the decoding solution of the mid-way decoding solution is quite strong, and I think it's probably not necessary in most cases. Like, if you think about the decoder of the color code that starts from the color code and goes to the surface code, it doesn't actually preserve the min-weight solution, but it does preserve things you'd want, like you have a threshold on one side, means you have a threshold on the other. And so at the moment, I'm actually working with Abhishek and Lucas, who are here, on kind of looking at this and relaxing this and seeing what we can say about preserving decoding structure with this formal language. And then the last thing is that it would be very nice to think about non-Clifford circuits in this kind of framework to analyze, like, you know, cultivation or distillation circuits. But then it's kind of difficult because now, okay, if we want to do like a detector error model or a space-time code for a non-Clifford circuit, then I don't really know how to handle this fully because now I need to think about, so if I have, like, let's say I have a circuit with T gates, then what this is going to do is that if I think about the propagation through a T gate, my X operator propagates to an X times S operator. So now I have some Clifford operators in the circuit, and so now I need, like, to have a formalism for subsystem codes generated by like Clifford operators. And so I'm kind of currently working a little bit on this first steps with some mathematicians from Guelph, where we're kind of trying to think about extensions of the XS formalism, basically the XP formalism in this kind of direction. And eventually it'd be kind of nice if we could also apply these analysis tools to non-Clifford circuits, but there's still some like more basic notions we need to get sorted out first, I think. Okay, so yeah, thanks a lot for your attention. I just wanted to, so that's the archive link for the paper if you're interested. And then I wanted to thank my collaborators. So Arthur Pesser, who's just finished his PhD at UCL, did the lion's share of the work on this project and really did a lot of amazing work. And then also had also a nice collaboration with my former colleagues at Xanadu, Austin, and Milan. Thanks a lot.
Thanks very much. Questions? Don, you got it first.
Yeah, a question about this like minimum weight encoding solution. Are you assuming that's like unique, or what if there's degeneracy? Couldn't you have like one you have something that's two like inequivalent minimum weight solutions, like one could come down, the other one could go up.
Yeah. So actually, I think we need to update this in the next version because it's that we didn't actually consider this issue and it's something that Abhishek raised with me. So I think you can fix it, but you just because then the problem is that it might not be like deterministic the map because if you just like you have like a set of minimum weight solutions, you just pick a random one, but then what if you pick a different random one and how do they map? So I think you can take care of it, but it is kind of an issue with the current one. But I think it's like now I'm pretty sure this is like too strong what we require here. I think it's much more interesting to relax the definition and to think about like just preserving the threshold or basically preserving the fact that the error plus recovery is in the trivial knowledge class.
Campbell first.
Thanks for the nice talk. So yeah, you mentioned threshold a couple of times, but you were specifically trying to preserve the distance, right? And what can you say about like whether or not there is a threshold or whether or not it's preserved? Is the existence sort of? It looked from the Bacon-Shore example like you could sort of introduce a threshold or something like that through some of these processes.
This is as you say, like the Bacon-Shore code, it has like no threshold, we know that. But this is kind of an artifact of using this phenomenological noise model here, because in that noise model, I have no real penalty for having high weight checks, because like all I'm assuming is that I have a perfect measurement of the check and then like a measurement error potentially. So in that model, it would have a threshold. So there's not. It's just an artifact of the noise model. But in general, like I would just want to point out that we didn't actually show, using these fault-tolerant maps, we didn't actually prove anything about, oh, if this code has a threshold, this code has a threshold. And we just proved the stuff about the decoding problem and the distance. But this is something that we actually are looking at the follow-up work, which we have to have a chat about this week. But exactly if you kind of relax this definition, and then you kind of, you probably want to enforce some kind of sparsity on the chain map, and then you should be able to prove that you have a threshold on both sides. And this is sort of what they actually do in the qubits of Delphos paper, is that really they're describing the chain map and then they prove that it has this threshold resolution.
I have a question regarding the circuit level noise model. So I would guess that's similar to like STIM handles circuit level noise model, that if you still have independent Pauli channels on some of your gates, this would generalize pretty straightforwardly.
Yeah.
What about more rich noise models like correlated noise or erasure errors? Do you see a way to introduce them in your framework?
I think my feeling is, I haven't thought about it in detail, but my feeling is that if it's possible to think about those noise models in a stabilized code or using a STIM simulation, then you should be able to introduce it here. I mean, I know that you can think about erasure errors as like giving you a distribution over Pauli errors, and so I think you could just impose that on these circuits, for example. So I would say that anything you can do with kind of your STIM simulation, you should be able to formalize in this kind of language.
In this thing about threshold preservation, you mean preservation of some finite threshold? Do you want the actual value to be the same?
So what they showed is that like if there exists a threshold on one side, there exists a threshold on the other side. So just that, and then I think the color code they actually can prove something about the value. But I think that probably comes from maybe the sparsity that we can get as well. But I have to look again exactly. But I know for sure you can say the existence, and then in certain cases maybe you can say something about the value.
You mentioned weakening the notion of chain map. Could you give like a kind of a vibes-based intuition behind what's going on there? And
I think I'll probably have to discuss it with you offline. But yeah, I mean, it's just because of like this rule, the rule. The thing that becomes the problem, is this rule A, because it's like, so going this way, it's kind of like clear what I should do, but going this way, it's like, where does the error map? Does it map to like this one, or does it map to this one?
Mm-hmm.
This is the issue, basically, that means that it's not kind of like a chain map anymore.
Mm-hmm.
And so then, but then we show that basically I mean, we made up some definition that doesn't, we couldn't find anything like this in the mathematical literature, so we just had to write it down, but it involves some condition on the matrices, but I think it's just better if I sit down and show you.
Yeah, I'm curious whether it has something to do with like maps between isotropic spaces and stuff like that and symplectic things.
Yeah, it'll be good to discuss.
I have one quick question, which is, so you found these two rules,
Yeah.
and if I understand everything is built out of that.
Yeah.
Is there any hope that there might be additional rules within this framework, or do you think that these are the?
Yeah. Again, excellent question. And so I would say, so actually these rules we found, they're kind of like, they also appear in very similar form in this work of the ZX calculus people of Ben Rogatz and others. And so they have some ZX rewrite rules that look a bit like this. And they had a nice paper out like a few months ago on the completeness of those rewrites. So I think in their case, what they understand is like, they have a complete set of fault-tolerant maps, basically, and then they know they can express any other in terms of those. So I think you probably could rephrase their results here. And I think they are quite analogous, because they use this kind of what they call a CSS noise model, which is again basically some phenomenological XZ model. So I think it's really equivalent. And so I can't remember exactly what the rules are they have, but they're simple enough that you could write them on one slide, the complete set.
Right. Okay. Are there no more questions? If there are no more questions, let's thank Michael again.